All right, so we're going to cover latent curve modeling or latent growth models in this section, which to me are really interesting models that allow you to take longitudinal data and understand what's happening in it. So the point of a latent curve model, or more commonly a latent growth model, is that it measures change over repeated time measurements. And so another option for a repeated measures kind of design is ANOVA, or a multi-level model. And I would say ANOVA is probably the least useful in the sense that it gives you, time 1 to time 2 and time 2 to time 3 and maybe 1 to 3, but doesn't give you an overall trend for the data. You can use a linear post hoc analysis to determine what the linear trend is. You can use a multi-level model to determine trends across time as well. And it allows you to do a little more than an ANOVA because it allows for random intercepts, which we're going to cover here in this video what that means. So this is kind of even a step up for that because it allows me to test concurrent models against each other to determine information about those random intercepts and slopes and how that works. Another thing is that it actually will let me look at the issues with sporicity. So remember, in a repeated measures design, sporicity is this idea that the variances between time points are the same, and the correlations between time points are the same. And that's often a really hard assumption to meet because let's say you're doing a weight loss program, the data naturally tends to regress towards the bottom. And then even in, let's say, exams, sometimes they tend to regress towards the mean because people's scores if you're at the top, you can only come down. If you're at the bottom, you really can only come up. And so you have problems with the variance contracting over time, or maybe if you're making a task more difficult, expanding. And this, to me, really allows you to look at that. It also kind of looks at heteroscedasticity. So this is an interesting design because it allows me to test linear trends over time and also to test some ideas with assumptions and sort of define them a little more. And we'll get into that a little more as we go through the different types of models that you can do for this. Okay. So it can give you more information than a repeated measures design. They also can be way more complex, but not so much if you have multiple variables that you're interested in. You can do 2 sets of slopes, but the interactions between those get really complicated. So it is a means and covariances model, just like a multi-group model. So we're going to estimate means and covariances and not just covariances. We're going to estimate those observed values, so things like residuals, and unobserved values, the slope and the intercept. Although it seems weird to say they're unobserved, those are going to be our latent variables in this example. And you can't really get those unobserved things in repeated measures. I mean, you sort of can with a multi-level model, but this I feel like gives you a little more information. So some assumptions. This is actually true of all structural equation models, that the latent variables are continuous, but also in this particular example, the manifest variables are continuous. So the continuous measurement of the DVs if we're going to continue to use maximum likelihood estimation. And then the big one is that the time spacing is the same for people, not for time points. So you could test people at time baseline, right? Go 2 weeks, and then the next one be 4 weeks. So that's an uneven time spacing, but that's for the levels. The spacing for people needs to be the same. So you can have some participants that test at 2 weeks and some that test at 4 weeks, and you count those as the same time point. So the spacing for participants needs to be the same for each of those levels, because that is one assumption with the way we're going to code this, is that each person's taking the time points at approximately the same time. Obviously, there's a little wiggle room. When you're doing longitudinal data, it's sometimes hard to get people all on the same day, but a little bit around those times is okay. You have to have at least 3 time points per person, otherwise it's just dependent t, and so don't do this really complicated design. And you do need very large samples, so that's one restriction, is that at least with multi-level models you don't. That's one good thing about them. Is with repeated measures designs, is smaller samples can still give you a lot of power because they're repeated, and so it reduces error due to the fact that you understand the individual differences in participants. However, this is still SEM, so it still needs a lot of people to make this really work appropriately. Alright, so before you start one of these designs, what you really have to know or be theorizing is the type of change that you're expecting. Do you expect it to be linear, or do you expect it to be curvilinear? Generally, these models are called linear growth or latent growth models, and we expect linearity. Now, the book calls these latent curve models, which I find kind of interesting, because that implies that it's a curvilinear or maybe a power function. So we always joke that the learning curve for R is a power function, where it feels like you can't learn anything and just so much stuff, oh my god, and then you level out. But the idea is that you can do power functions or x squared functions, or even sort of weird 3 cubic functions, as long as you have enough time points to test those. Okay. We're just going to focus on linear designs because they're the easiest starting point, but you can estimate in a curvilinear or power function way. Alright, so this is from the book. I think this is from the Byrne book. And so it was just an example of what one of these models looks like when you diagram them. But I have a better one on the next slide. But the idea is that you have two latents, one for the intercept, one for the slope, and then you'll have paths from those latents, each one going to the time points. So here are 3 manifest variables that we've measured, time point 1, 2, and 3. And then the path coefficients are actually going to get set to specific values. So let's look at a little cleaner version. It's a little easier to read. Okay. So we have 3 time points for this example. The intercept value and the slope. They are going to be covaried in some of the models. And you'll see that here for the 3 intercept coefficients, they're all set to 1. What that does, and I'll have this on a slide in a second, is that it sets the intercepts so you only get 1 estimate. Because there really is only 1 intercept in a linear growth model. And it's the y-axis point or the start point. So by setting these to 1, we are helping with identification. And we're forcing it to give us 1 score. So it'll be the average starting point for time 1. For the slope over here, we're going to set those coefficients as well, but not all to 1. Generally, the first time point is set to 0, and then the next 2 time points are set to something that approximates the time difference between them. If it's equal, 0, 1, and 2 are very popular. If it's unequal, I would suggest making the pattern match what that inequality is. So if you have something at 0 time 1, and then 2 weeks, there's time 2, and then 4 weeks, you could do 0, 2, and 6. Because the space between 2 and 6 is 4 weeks, 0 and 2 is 2 weeks. Okay. That scaling doesn't, you could also do 0, 1, and 3. Like the scaling doesn't matter so much as long as the separation between points approximates the time difference, so that it knows that the math can calculate that this is an even space 0 to 1 as 1 to 2. But if it's 2 weeks in one and 4 weeks in the other, it needs to know that that's a longer space or a bigger difference. The other thing you're going to see is these zeros up here and these zeros here. So we're going to constrain the means of these items to be 0 because we're forcing the mean, the intercept value sort of over here, and the slope value, so the average slope over here. So this just helps control, and so we don't get an average for each question. The average for the first one goes to the intercept, and then the change between them goes to the slope. And we also can constrain the residual variances, or residual means to 0, and just look at their variances. So it is a means and intercept model, but the only means and means and covariances. The only means and covariances that actually get estimated are down here. So all of that now on some slides. So we're going to set those regression loading values to specific numbers to estimate the intercept and slope. So these are your path coefficients. The intercept values are going to be set to 1, indicating I don't want to estimate them. So these values are not going to be, there's going to be no B values basically. And by doing that, it gives us a start point for the first time point. And essentially, that's the average point where people start. So that's the y-intercept. And by estimating this value, it gives us sort of an overall score that this is what people score at time 1 in general, so on average. And that's the same way an intercept works in a regression model. And remember, it's the y mean. The slope value is going to represent the change over time. So this could be positive, it could be negative. And then we're specifically doing linear models. So we can set them to anything we want, but usually the first time point is 0 for baseline. So there's no slope at time 1 because you have to have 2 points to get slope. So you can't just have a slope of 1 dot, you have to have at least 2 to get the difference between them for slope. The rest of the paths are set based on those time differences between them, like I've already talked about. So why would we do this? Well, by setting those parameters in that particular pattern, it helps us with identification. We're going to have lots of degrees of freedom because we're not estimating very much. Sometimes it's only 1 or 2 things. It's a match to the concept of slope. I wouldn't want 3 intercepts because it's a change over time. It doesn't make sense to have 3 slopes and 3 intercepts. And it allows you to not have to set the variances because that's what we're actually going to be interested in are the variances for the intercept and the slope as well as the intercept and slope estimation. So we're actually going to look at the intercept itself, but also the spread around the intercept. So this will be kind of a new concept because we don't normally talk about this. We know that the intercept gets a standard error value, or you should anyway, but we don't ever really consider what that standard error means. We just kind of say, well, it's the intercept. Is it greater than 0? Great, moving on. Or it's the slope. Is the slope significant? Awesome. But sometimes we don't talk about the spread around them, and this analysis really focuses on that idea. So some questions that we can answer with a latent growth model is what is the average change across people? So how much are they going up over time or how much are they decreasing over time? And so I'm really going to use an example of exam scores just because it's an easy thing to conceptualize. So if we have 4 exams, how much do people get better or are they getting worse? So one problem you'll have with this type of design is if people kind of go up and then down and then up and then down, because that is not a linear change. That starts to become cubic. Or if people go up at the beginning and then they go down at the end, then that's going to be curvilinear. So it helps if you sort of plot this data beforehand and look at either a dot plot of each time point by that DV score or even a bar chart of them and kind of look at the change that you're expecting. You can test them against each other. Those models tend to be the same degrees of freedom, so often you have to use AIC or ECVI to test which one fits better, but the errors will also give you a good clue which model approximates the data better. So you can test linear models versus curvilinear models for each person. Each design. But one thing that you'll want to do, I always just graph the data first. So where do those people start? That's the intercept. How does that change? That's the slope. And then what is the form of the change is the type of slope that you maybe should be using, either linear or curvilinear. So some more questions. So is the average slope and the average intercept, is that a good fit for all participants? Or should we include the variance to account for differences between people? So when you include the variance for a slope and an intercept as part of your model, it's called a random effects when you add those random variances. So what's happening is you're allowing the intercept to vary across participants. And so back to our exam example, some people are C students, and some people are A students. So the change over time is influenced by where people start. And so if I have C students and A students in a class, I could get out an average and say that the starting point is a B, but that doesn't necessarily represent the data in the best way. So if I say, okay, well, I'll let people vary along that intercept, it captures the spread of where people start better. Now, random slopes may or may not be a good thing for you. So a large variance on the slope estimate is often considered bad, because that means that the slopes vary a lot, so that your estimate of slope is not very believable. It also allows you to think about other things that could be influencing the slope. Okay. So random intercepts are often a good thing for you, not because they're good that people start kind of all over the place, but we are dealing with people generally in psychology, and so having a way to control for those individual differences in start really allows us to test if our manipulation of the data, or the thing that we have measured across levels or across time, is really what's influencing, or if it's all just kind of a random effect that people are going up and down. So if we use a random effects model, especially that random slope, and it is significant and it varies a lot, maybe there's another variable that really explains those random effects. So I could use previous GPA, ACT score, or some measure of aptitude to control for that random intercept, because that would help me understand why some students are A students, some students are B students. So I could use a mimic model, or just another influencing variable, so kind of like a covariate and then ANCOVA, to explain why that random effect is significant. Additionally, if I have random slopes, maybe there's another variable that's involved that changes the slope for some participants but not other participants, and that's a moderation analysis. And so that's where we get into interactions between the slope and this other variable. And so what you can see sometimes is, like, if you've seen, and I know you guys have, those fan effects pictures that you get out of moderation, where some slopes are different levels. That might be what's happening when you get a random slope, significant random slope variance. And so maybe you know what that other variable is, and you can include it in your model. All right, so a little bit on the output. The example will be in the next video, but what does all this output mean once I finally get to look at it? So you're going to get an intercept mean, and so it's going to say in the output intercept mean. Don't let the word mean confuse you. It is the intercept, so it's the average starting point for time one. It's just called a mean because of the type of model that we're estimating, so means and covariances. The slope mean is the average increment across points. So by my 4 example, I have 1 to 2, 2 to 3, and 3 to 4. But instead of getting 3 estimates for those, which would just be pairwise comparisons, it gives me the average increment across all of them. And that's why it's sort of, you have to look at the data, because if it is flat from 1 to 2 and 2 to 3, but from 3 to 4 it increases, that's actually a nice curvilinear function. But if you're using a linear model to estimate that, it's not going to look very interesting, because it's going to be fairly flat, because the first couple of time points are flat. But when you're looking at the output, the slope mean is that average increment across from 1 to 2, 2 to 3, and so on. So the intercept variance, and I tried to draw you some really sad-looking pictures down here, but intercept variance is sort of an interesting point. It's the spread around the y-intercept. And so if this is our y-intercept here, it's how much we expect the spread to be here. Now, it is not the range, it's a variance score, so it's kind of the average spread around that starting point. So it's the average spread around the average. So if I have a class full of A to C students, and I come up with a B average, it might be 5 points on either side. So larger scores indicate a lot of spread, so people start in a lot of different places. Smaller intercept variances indicate a small spread, so people start all in about the same place. And that's interesting to know, because it could be that for some designs, everyone starts equal, and then they get further apart as you go. And so we'll have a way to estimate that as well. But that would be heteroscedasticity, right? So small down here at the top, spreading out to the bottom. But we'll have a way to look at the residuals for each time point. So this here will only tell me about sort of time point 1, if there is a small or large spread around it. Often this is going to be a significant addition to your model because it helps to know that the people have different start scores. So unless everyone's like pretty close together, this model tends to be a good change for you. Now, slope variance is kind of a different story. It's the range of increments across time points. So this is not the best picture, but here's an idea. So slope variances indicate just differences in slopes. If I did each person individually, what slopes would I get for them one-on-one, and then that's the variance, and then the slope average is all of them taken together. And so this would be a small variance, where most of the slopes are very similar to the average one, which is the black line here. So the dotted lines might be different slopes for different participants, but they're all pretty close to the same. On the right side here, this is a large variance. So the straight line here is the slope that we estimated overall, but some people are still positive, some people are even steeper, some people are flat. And this means that the scores are going up and down kind of in different patterns for different folks. And this is where we get into an interaction in a sense. So if you had another variable that you thought explained that effect, where lots of people have this flat slope and then lots of people have a steeper slope, that's a good clue that you've missed a variable that interacts with time here. And so it's not just the fact that you've measured it 3 times, it's also this other variable that is affecting how they change over time. So maybe sometimes this latent curve or latent growth model shows you that you're missing something. Now knowing what that is may or may not be easy. Now to me, the trickiest 2 things of these models to understand is factor covariance and residual errors. So we're also going to estimate the correlation or covariance between intercepts and slopes. And this seems a little odd because normally we wouldn't talk about how the intercept and slope are related. In a perfect world, they're not related. My start point has almost nothing to do with how much I'm going up or going down. It just is my start point, and then here's how much I'm going up. All right. Now, if I have... This is the hardest part here. So if you have a positive covariance, remember that positive correlations indicate that high scores go with high scores and low scores go with low scores. So people who have high scores have higher intercepts. Higher slopes. So if I start high, I have a steeper slope. So high slopes mean that they're steeper. If the slopes are positive. So high intercepts are tied to high positive slopes, so people who start high go up faster. Positive covariance and a negative slope, I wrote this down here, is people who start high go down faster. So it's still a high intercept tied to a high slope, it's just that slope is negative. So if I start a high, I am decreasing faster than if I start low, we're decreasing slower. Okay? So high intercepts are tied to steeper slopes is probably the better way to think about it. If I switch this and I have a negative covariance, that means that people's high intercepts are tied to lower slopes, so flatter slopes, things closer to 0. So this is positive. People who start high go up slower because it's a fairly flat slope. If it's a negative covariance and a negative slope, right? People who start high go down slower. Okay? So high intercepts are tied to a low slope, but it's a low negative slope, so they go down slower than people with lower intercepts. And this is one of the hardest things, I think, in interpreting the output, just because it is kind of complicated. So I've written all the combinations down here on the slides for you to have. So what we're going to do to estimate this in R is the growth function. The great thing about that is it sets up the latent curve model for you and estimates those, or sets those specific regression coefficients, so you can't really do it wrong. So it creates that model picture for you and helps you set the right things to the right numbers. You can change them, so with the slope estimates, I could change them from 0, 1, 2 to something else, but it often helps you kind of get started. All right, so what we're going to do is we're going to test several different models here. Sorry, the dog will not leave me alone, so I'm petting with one hand and directing stats with the other. And the way that this works is very similar to a multi-group design. So in multi-group models, we started with the least restrictive model. So we just said, here, everybody be the same pancake, and everybody be, the estimates are free to vary. And then we slowly got more and more restrictive. Hi, puppy, go away. And so we got more and more restrictive. And as we got more restrictive, we were trying to see where the model would break to indicate that the groups were no longer different. So in this particular set of models, what we're going to do is start with the most constrained, so the model with the least number of parameters, and slowly estimate and add parameters to see which model's best. So we should expect that these models should get better as we go, whereas in multi-group analysis, we expected the models to get worse as we went. Okay. And if the models are getting better, that's good. That means that adding the parameters was significant and important. Okay. We would prefer, this is going to be model 4, the unconstrained model to be the best, which implies that the slope and intercept parameters are useful, but the variances are low. Especially model 3 to model 4, because model 3 is a random slope and model 4 is a estimated slope. So you really want your slope parameter to be significant, because that's the point of these models, is to have a significant change over time. So to me, that's the most important piece of where we're going, is to have the slope parameter be significant. So starting with the first model, what we're going to do is do an intercept-only model. If you've ever gotten to do some MLM models, this is a very similar set of procedures, actually. And so you start by estimating the intercept. So there's no slope parameter at all. Okay? And I did a very bad drawing of this down here. You want this model actually to be bad. At the moment, we don't have anything to compare it to because it's the first model, but if the fit for this model is poor, that is okay. If this model is the best model, that's not a good thing for you. Because then you're saying that the average score is the best for all time points. So here are our exam scores, so 1 through 4, and here's the exam. And basically this would say everybody got the exact same score on the test, which never happens, across all 4 exams. So everybody made an 85 every single time. Okay. That's so unlikely. And so if that's happening in your model, that means literally nothing changed in your model, in your experiment. You're going to constrain the intercept variance to 0, so you only get a mean score. So there is going to be variance here, but we forced it to be 0. So this is why it tends to not fit well, is because there's, if you have no variance, the stupid thing's not going to run, first of all. But if those variance is really almost 0, that's just implying that everybody got the exact same score. Okay. Our residuals, our error here, is going to be forced to be the same. Now we're still going to estimate the residual term here. So the intercept variance is 0. So instead, all of that variation across time is forced into the residuals. So we would expect the residuals here to be higher. So they should be highest in this model and lowest in the last model. Because basically, instead of estimating the range around the intercept or any changes from flat, we forced all of that into residuals. And so those residuals are forced to be the same, though, for every single time point. So the variance is estimated the same across time. And that is sort of an issue with sporicity. Remember that sporicity assumes that the differences between time points are the same, or effectively a homogeneity idea that the variances are the same. And if they are, great, but if they aren't, at the moment, that the way we're estimating is going to be rather poor because it's forcing them to all be the same. All right, the second model, it's still an intercept-only model, so still no slope, but we're allowing the intercept variance to be greater than 0. Okay, this is variance, so it can't be negative. But we're basically saying, okay, some people's scores are going to vary around that average. Some people are going to be higher, some people are going to be lower. Okay, so this is a random intercept model, and essentially takes this line here and says, well, some people can be 2 points up, some people can be 3 points down. Still, you wouldn't necessarily want this to be large differences between people, but you'll see that this will change slightly as we add more parameters, because right now we're still estimating a very flat slope. So we hope that the slope is not flat, but we're going to allow people to start in different places. The residual variances are still estimated to be equal. Those don't come to last, or we can let them be different, and there's still no slope. Now what we're going to do is test these models against each other. We can use chi-square to see if how they're changing, and we would expect the models to get successively better. The other thing you expect to see is that the residual variances should decrease, because what's happening is as you add more parameters to the model, those errors go from being residuals or error to that parameter. So instead of assuming that everybody's exactly the same 1 point, everybody's made an 85, we've allowed some people to make 60s and some people to make 95s. Will you get down? Because we've allowed them to vary, that no longer is error variance, it's now in the variance for the intercept. You're such a spoiled brat. All right. So the third model is a random slope. So it's okay if between 2 and 3 this difference isn't significant, because really it's between 3 and 4 you want it to be significant. You would assume that by letting the slopes vary, you're going to get better than no slope at all. So often it is significant, but I would argue that making it an average slope of 0, I don't know, we'll see. In theory, it could not be different and that'd be okay, but in practice, it's probably going to be different if something happened in your experiment. Okay. So we're going to use some extra code here to set that slope to 0. So we're adding the slope in, but we're setting the actual slope parameter to 0. So you still want this model to be kind of bad, because the slope should be something different than 0. We're also going to uncorrelate it between slope and intercept. We're going to add that parameter in later. So right now we're leaving slope and intercept uncorrelated. And we're leaving in the intercept and its variance. So we're adding this to the model. We're not changing the second model. This is an addition. And we're still keeping the residuals constrained. So really what we're doing is letting the slope variance be estimated. And so this variance hopefully is greater than 0. But we're still forcing the slope to be 0. Okay, so we're just saying like there's going to be some change across time, but the average change should be 0. Now that might be a problem if the change is 0, because some people are positive slopes and some people are negative slopes, so that average is 0. So this model will look really good because it's measuring all the variance where some people are positive and some people are negative. But then the slope really is averaging out to 0. That's like a perfect interaction where some people are going up, some people are going down, so it makes a perfect X. And in that situation, you really have to figure out why some are going up perfectly and some are going down perfectly. Okay. That fourth model, this should be the best model, was we're going to allow our slope and intercept to vary. And so we're adding the slope mean. And so this is where you're finally going to get the estimate of how much people are going up or down across time. We're still constraining those residual variances. So this is where you have, where did they start and how much did they go up? And so a unstandardized model might be the best way to look at this, because then it's still in the scale of the data. A standardized model will give you the covariance and a correlation style, but really for our purposes, we want to know if it's positive or negative when you add that double-headed arrow between them. But this should be the best model, where you've allowed the slope to be what it is, but you want the variance to be small. So remember, small variances around the slope, especially if they're non-significant, would indicate that the slopes are all the same for participants. Now, if you're wanting them to be different because you have some theory about why they may be different, then the variance term should be larger, and it's just adding in the variable that predicts why they're different across time. So this model should be the best model, and hopefully the fit indices for this model are good. You still have to be concerned with having a good fitting model, so all the rules we've been talking about for fit indices all semester. The other concern that you have here is that it's significantly better than the third model. The last model we're going to test is a totally unconstrained model, and you let those residuals vary. So we want our residuals to be small. With every addition of a parameter, the residuals should be getting smaller, and we'll make a table for this so that you can see that. And then we'd hope that they be equal. So we're estimating the same error at each time point, which is just a little bit of like people are weird. And so in theory, models 4 and 5 are not significantly different. In practice, that doesn't always work, right? Because of heteroskedasticity or sporicity issues. And it might be that you know why there's a big change for let's say exam 4. Maybe it's because, in my undergrad class would be exam 3. It's one of the most difficult ones. And so people tend to vary a lot more than exam 1. Just because with exam 1 we're doing very simple terminology and most people can memorize the terms, but by the time you hit exam 3, we're knee-deep in t-tests and ANOVAs, and people just have a harder time with hypothesis testing, so you get more variance at that time point than time point 1. So I would expect this model to be significant, but I have a good reason for why the residuals are changing over time. And I would hope in some way I might be able to find a way to predict that, maybe with exam difficulty. Okay. So altogether, that is a way to estimate latent growth models or latent curve models, where you can look at intercepts and slopes, random intercepts and slopes, and figure out the different pieces and how they work together in your experiment.